that the last one, if f is injective, then you see this properties little bit we need to understand more properly, because this is relating to the inverse. Look, the last properties, number 5, actually in my case, number 5. If f is injective, which means 1-to-1 injective, then the composition of f and f minus 1 acting to the x actually is x for all x from d of f, the domain of f. Pay attention. Then another interesting things, the f, the composition of f and f minus 1 of acting x is also x, but for all x from RF annotation. Annotate, share it. What happened? Is it okay? So please pay attention. F minus 1f equal to x. The inverse actually with f, usually we call it identity operator. Identity operator acting to the any function is the same function. So this one is okay. This one is okay. But you see, the composition of f and f minus 1 actually is x for all x from df domain. A second one is on the RF. The same equation hold for all x from RF. Can I give one example? So because this one, I just want to conform with the example. Let's say it should be the to be exist of the inverse function, it must be injective function. Okay, so let's say I will take as a f of x as sine x. Sine x is the injective function. Okay, and gx I can take as x plus 1. Okay, just like this, x plus 1. So now actually no, I need to find the inverse function for the f. Inverse function for the f. Inverse function for the f actually is equal to what? F minus 1x actually is f minus 1x is arc sine x. Okay, arc sine x. So please pay attention. Arc sine is x. So here domain of x is df domain is R, any x. So here I need the range. Hey, please listen. This one is having some problem, you know. So actually, if I consider this one as a function, so here x taking value, you know, x taking value from -1 to 1. This is the domain. So domain of f minus 1 actually is -1, 1. What about the range? You remember range RF minus 1 is from minus infinity to plus infinity. Okay, so y varies from minus infinity to plus infinity, or we can call it r. So this is a range of f minus 1. Now, what about the composition? Hello, please pay attention. So what about composition of f, the first case? The composition of f minus 1 fx, fx. So it is f minus 1 of f of x. Okay, so this is arc sine of sine x equal to x, because of, but here what about this x actually should be in the domain of f. Arc sine sinus x actually equal to x for all x from R. Is it correct? This function actually is defined everywhere. So which this one is domain of f function, domain of f. It is correct. Look, domain of f is R. Domain of f is R. So here it is correct. This one is getting the from there. Now what about second one? Okay, so the second case, f, the composition of f minus 1 and f of x, which is f of f minus 1 x, actually giving sine of arc sine x equal to x. But this x now varies on the RF. So RF, what does it mean, RF? So for the given function f sinus x, RF actually is minus 1, 1. So this is the range of f. So here, this x, the inverse, function x, varies from minus 1 to 1 actually. Can you see the difference between these two important properties? If f is injective, then of course this composition function is a injective because x is a injective function. But for all x from df, df is domain of f is R for this case, domain. And range of f actually is minus 1 to 1 because sinus function we know. So both of them, you see, the domain of f and the range of f. So the domain of the composition function totally changes. Hello? Are you hearing me?
Yes, sir.
Why you are writing so much? Just listen me. Okay. So please pay attention. This is a big differences, on the composition function. You see, composition function is also injective. In both cases, they are injective. But in the first case, it varies. The x varies in the domain of f. In the second case, it is a range of f, which is minus 1 to 1. You see? So that's the interesting point. Okay, now let me explain the equivalent set. Actually, equivalent set very much depend on the bijectivity. So a set A is equivalent to the set B. Express it symbolically A and now equivalent sets. Equivalent sets. See, when we say that two sets are equivalent, so in the do you remember in the calculus also we have equivalent sets, but in the we say in the calculus two sets are equivalent if and only if every element of A is a element of B, and every element of B is the element of A. So this is the definition in the calculus. Okay, in the calculus. Here, equivalence comes from the bijectivity. Look, definition 1. A set A is equivalent to the set B, expressed symbolically A and B. This symbolic. If there is a bijective function, if there exists bijective function, not injective, bijective function. Okay, if there exists bijective function, bijective function, bijective function from A to B, from A to B. So here you see, bijective function is important. If we are able to find bijective function for given sets A and B, then we say these two sets are equivalent. Actually, so this equivalentness is equal to that definition as well. But here the important one, we need to, if we are able to find bijective functions, okay, bijective functions, then these two sets are equivalent, A equivalent to B, okay, please. And this equivalentness of the set has three properties. First is the reflexivity properties. For any three sets A, B, C, reflexivity is, I think, very clear because the A is equivalent to A. So, of course, if the element of A is the element of A, algebraically it is very clear. But here in the proof, they say there is a function because we need to find the bijective function. So that bijective function actually for the identity function, okay, UA, mapping A to A with this function A of X is X. So there is, you see, because we found there is a identity function in for this, it, you see, maps every element A to the A, every element of A to the A. So we are able to find this type of bijective function, and this function is a not only injective, it is a bijective function. For the bijectivity, two conditions: it must be injective and surjective. Right? Injective is 1-to-1. Surjective is onto 1-to-1 and onto all. We call it correspond. Yes. Scroll up. What? You mean this? Okay. Okay, here. You mean this one, huh? Okay, any question here?
Okay.
Where? arcsine. Yes, arcsine. Sine of arcsine. Actually, you usually use this one. Actually, this is my actually sine minus 1 actually is arcsine. Arc. 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 Yeah. ARC. Arc sine. Correct? Z. Okay. This is R. My R actually. This is not Z. R. Oh. Okay. Okay. Actually, usually R not writing like this, right? Writing like this. Arc sine X. Yes. Okay. Arc sine. Okay. Thank you. Thank you. So should be like this, not my writing is like Z. AZC. Okay. Thank you. So now please pay attention. The first proof of this theorem is easy. What about now second theorem, the second part of the theorem 2.1? So here the proof of the second one, they say like this. Because here if A equivalent B, so let A equivalent B. It means there exists bijective function BF, bijective function, so bijective function F actually, bijective function F mapping from A to B. So according to the definition, A equivalent B, A equivalent to B means there exists bijective function F, actually bijective function F, just F, bijective function F such that mapping A to B. Now look, from here, I can make conclusion. If F is bijective function, according to the above theorem, F minus 1 is also bijective. Is also bijective. Is also bijective. But this F bijective actually mapping this bijective function, mapping B to A. Bijective function. You see, bijectivity comes from the above theorem. What we call it this? Look, if F is a bijective, this is the composite function. So where we had the if F is a composite injective function, then injective, okay, is also injective. Look, if F is a injective, F minus 1 is also injective, corollary. It is the corollary. If it is bijective, if any function F, the inverse from B is also function, if and only F is bijective. Okay, you see, this is actually from corollary 2. This is because of corollary 2. Because of corollary 2, F minus 1 is also bijective. But F minus 1 mapping from B to A. So it means every, since it is bijective, means it is a one-to-one and onto. So every element of B is an element of A. From here, we have every element of A has element, the image in B. So means every element of A is an element of B. Here, every element of B is an element of A. So that's why these two sets are equivalent sets. So equivalent is actually, as I told you in the calculus, will given very proper and easy to understand. Here, little bit difficult, but generally you can understand how we can. But you see, For the first case, we are able to find the bijective function a to a. So this is a function. But for the second case, we didn't find any function. We just used the properties of the bijective functions properties. Okay. So because you see, I'm saying here a is equivalent b. According to the definition, there exists f, function f, bijective function. Exists bijective function f such that a maps to the b. By the corollary to f minus is also bijective function mapping from b to a. So that's why if a is the first part, a is equivalent to the b, from the second f minus 1, we can make conclusion that b is also equivalent to a. You see? Now, what about the third one? How we can prove the third properties? If a, you see, the third properties actually comes from the composition function. So in this third case, since a equivalent b and b equivalent c, then there exist two functions exist. I can say f and g, two functions such that two bijective functions bijective functions such that f function maps, you see, f function maps a to b, and the g function maps b to c, and both of them bijective. Bijectivity actually brings to the equivalentness of the sets. So now the composite of f and g, composite function is also bijective. It is also bijective because of which corollary? Bijective composite function. Now this one comes from this for the bijective, the remark 1, number 3, if f and g are both bijective, then the composite of f and g is also bijective. Okay, so this one comes from what we call it remark 1.1. In the bracket, remark 1.13. Okay, so you see the proof is also the here in terms of, you know, the logic thinking is easy. We cannot find unique functions or the exact functions to be bijective, but according to the logic thinking, we can come up with the solution. Okay, so for the third case, this equivalent set of the third case, we use composite function. A equivalent b, b equivalent c, then a equivalent c. So a equivalent c means there is a bijective function, composite function, bijective composite function from a to c, Okay, so that is a proof of this theorem. Then now the possessing these three properties is referred to as equivalent relations. Equivalent relations. So now next is a set A is finite if it is empty set, or if there is a natural number n such that A equivalent to this set. So now look, actually in calculus and here also there is differences. There is differences. You see, in how we name it in the calculus, the set is finite. Okay, set is a set is finite and is finite if element of element, the short, I think if I'm not mistaken, element of A is if element of A is countable, but countable actually can be, but it is still finite. It is countable. I think this is the correct, because look, countable, then number of look, there are two types of the. For example, if I take this interval, is this finite? Look, the 0, 1. Hello, look at me. 0, 1 interval is finite or not finite?
Finite.
You see. Okay. Currently, actually, this one is uncountable. This the element in the 0, 1 is uncountable. Is uncountable. Okay, we cannot count. So it means we cannot find the equivalent set with this 1, 2, and etc. n. We cannot, cannot find the equivalentness between this interval and this set. Okay, so the currently what they say is a set S A is finite if it is empty, or there is a natural number n such that A is equivalent with the natural number set. You see, A, if the equivalent set to the B, which is like this. So this is the finite set definition. Okay, finite set definition. You will see the which set is finite, which set is infinite. Okay, so from the below we will see. I think here this one is uncountable, which is it. Another finiteness, actually, it is a boundedness. You see, there are two types of finite set. One is bounded set. So A is actually is a bounded set, but it is element of A is uncountable. So that's why you will see. So what we can say about this set, after knowing the definition. So okay, the cardinal number, cardinality of A. Okay, you see, A is infinite if it is not finite. This is a short definition. A is infinite if it is not finite. A set A is finite if there is an empty, if it is empty set, or if there is a natural numbers n such that the element of A can be counted by the natural number. So here you can see that if A is an empty set, then cardinal number of A is 0. If A, this is cardinality of A. If A is equivalent with 1, 2, and n, then A has exactly n elements. You see, A has exactly n elements. So it can be counted by the natural number set. Actually, this one shows that element of A, can be counted by the natural number set. Okay, if it is countable, then we say it is a finite. So now, what for any two finite sets A and B, it follows that it follows from the transitivity if and only if the cardinal number of A equal to the cardinal number of B. So now you see another definition. So two sets are equivalent, A and B are equivalent if cardinal number of A is equal to cardinal number of B. There is a result to also hold for the infinite sets. But you know, if A is a subset of B, then cardinal number of A is also less than the cardinal number of B. So now how to find the cardinal number, you will see. Hence A, B are not equivalent. They are, because for the equivalentness, so cardinal number of A must be cardinal number of B. This relation, the relation partition finite sets into the equivalent classes. Okay, correct. The second result is not necessarily hold for the infinite sets. Okay, example. For example, the N1. If we have natural number set 1, 3, 5, 7, and etc. You see, this set actually element is not finite, but still it is called this set is a finite. Finiteness comes from the countable sets. Okay, finiteness comes from the countable set. So this set be the of or all odd natural numbers, and N2 is all be the set of all even numbers. The bijection function, now you see, for these cases, we can find bijection function like this. Okay, very interesting point. Please pay attention. Now, the set A, okay, now in this example, look, set A is a set of odd numbers, A, 1, 3, 5, and etc. And second one is even numbers, 2, 4, 6, and etc. Okay, so for such kind of natural number set, we can find bijective function Fn as n plus 1. You see, Fn plus 1. So this is for the case A, f of n equal to 2n for the second function, for the second set. You see, we are trying to find bijective function. Bijective function. Now, can you see, if we are able to find the bijective function, then these two sets are equivalent. So I'm going to prove this. You know, the A is equivalent with the finite natural number set. So look, for the A, for the first case, so this is the function implies N1 equivalent to the N2. Okay, so actually here they are trying to show this A and B are equivalent under this function, You see, any element of A, I will take 1. So I add 1, I will get 2. Any element, for example, 5, I will add 1, I will get 6. So using this function, which is bijective, this function is a bijective function. We can show that A and B are equivalent sets. Even they, you see, here pay attention. The every element of A is not element of B. Hello, please pay attention. This definition is totally different than the calculus. In the calculus, we say every element of A is the element of B, and every element of B is the element of A. We say these sets are equal. But here, no, we don't say like this. Equivalentness actually depends on the bijectivity of the function. If we are able to find the bijective function between these two functions, then we say they are equal. Okay, now You see, this function is really a bijective function for this two. And also, what about the second function? The bijective function to n also implies n to the n2. N to the n2. Okay. Now look. Now, if I take this function, so that function, actually, that function maps, you see, the natural number set. We have the natural number set, 1, 2, 3, and etc. And I have n2, the only the even numbers. Okay, so for these even numbers, I can find the bijective function. How we know that this function is a bijective? Huh? How we know that it is a bijective? So this function. To be bijective, it must be one-to-one function and onto. Okay, look how I can check the bijectivity. Huh? So first, f of n1 equal to f of n2, which is 2n1 equal to 2n2, implies, you see, implies n1 equal to n2. So this is a injectivity. This function is injective function. Now, what about surjectivity? So actually, this function f maps from for that one df. Okay, df. What about df? Please help me. df. Okay, df is what for this function df? Huh? Df is for any n from capital N. Actually, df is natural number set, right? Here I can take 1, 2, 3, any number. So that is a df. And what about the range? rf, rf also, you know, rf also for any n, the natural number set. You see, there is no restriction for rf as well. So it is surjective. So injective and surjective. So it means df is equal to rf. Domain of f is equal to rf. So this function is bijective function, injective and surjective. It is a bijective function. So that bijective function makes here, they say here, this second function g actually maps g function in the number 3. So any natural number set maps to the n2. Any yeah, the gn is, so it implies n and n2 are equivalent sets. Look, actually n has more elements. Look, 1, 2, 3. We have all the elements of natural sets numbers. We have 2, 4. Actually, we are cutting or skipping the odd numbers. But in terms of equivalentness, these two sets are equivalent. You see how we found? We found the the g function, g of n function, which is, you see, this function just now I have shown it is a bijective function. If there is a bijective function between two sets, we are able to find, then these sets are equivalent sets. Even they, in real case, they are not equal, but they are equivalent. Here, please pay attention. Equivalent sets and equal sets. Okay? So we are talking about the equivalence. So equivalent is depending on the finding of the bijective function. If there is bijective function, you are able to find, then you can show n and n2 is equivalent sets. Okay, now next example shows what? So now next example shows that for example 3, Z, look, they are proving Z is equivalent with N. How we prove it? So we need to find the bijective function. If we are able to find the bijective functions, then we say these two sets are bijective. Now look, how they found bijective. So they found very nice function. Please pay attention. I will give one questions in the exam. Okay. So if on the equivalent sets. So for this case, they say to prove let F maps Z into N by this F of N is equal to 2N if N is greater than 0, and if N less than 0, so it is equal to minus 2N plus 1. Look, you see, the one function divides into the two. Now look, if N greater than 0, and taking the values 1, 2, 3, and etc. So what about this Fn? Fn, which is 2n, taking the value 2, 4, 6, and etc. Right? Okay, it is like this. Now, if n is less than 0, look, less than or equal to 0, then taking value is what? Minus 1, minus 2, minus 3, and etc. Right? So if it takes this value, so what will happen? I put, okay. Now, if it is so, f of n finding this minus 2n plus 1, look, 2n plus 1, then n equal to minus 1, what will happen? F minus 1 actually is 3. F minus 2 minus 2, 5, right? 5, and etc. You see, F minus 3 is 7, and so on. So look, here we have all even numbers, and this one gives all the odd numbers. Okay, therefore any n from n, so this f function actually gives what? All the natural number set n. It gives all the natural number set, which is, you see, like this: 1, 2, 3, and so on. All in integer, positive integer numbers. So now, how we assign, you know, all the negative numbers and positive numbers, we can assign Fn like this. Nice, correct. So note that F maps the positive integers to the even natural number and the non-positive integers to the odd natural numbers. It is if n greater than 0, Fn is n2, and this one Fn1. To show that F is an injective, suppose that Fn1, Fn. Now, what about injectivity of this function? How we show? Please pay attention. Here, there is some difficulties if you don't pay attention on the definition. Look, to show the injectivity, I will consider N1 equal to Fn2. Okay, now this implies 2N1 and 2N2. For you see, on the other hand, so here, which function I use? If N1, N2, N1, N2, if N1 is positive, I will use. So actually N1, here I will put this condition. Let N1 and N2 is positive. Under this condition, so f of N1 is 2N1 equal to 2N2. And from here I can get N1, and from here I can get N1 equal to N2. Injectivity holds. Injectivity holds. What about the second function? If this is case 1. So case 2, if N1 and N2 is negative, then this f of N1 equal to f of N2 implies, you see here, little bit pay attention that there is a case. You have, it is not stated here, but here I am stating 2N1 minus plus 1 equal to minus 2N2 plus 1. So 2N1 equal to minus 2N2. So it implies N1 equal to N2. In both cases, it shows that this given function is injective. So to show that f is a surjective, suppose the m belong to the N1 plus N2. You see, so if m belong to the N1, then there is a negative integer k such that m2k plus 1. In the case of f minus k, in the case of f, if m is 2k for some positive integer, then f of k is equal to m. Thus f is bijective. Actually, for the surjectivity here, you see, they are showing little bit different. For the surjective, df equal to rf actually. So please pay attention how they prove. Please, I hope you can understand. You see, surjectivity, they are saying that any m from n, which is n1 plus union n2, is correct. We are taking any n, m. Then if m belong to the n1, then there is a non-negative integer k such that m equal to 2k plus 1. In which case, f of minus k equal to m. F of, why it is called minus k equal to m? So only please pay attention, this one, if m belong to the n2, which is like this, it is correct for some positive. Then f of k, look, if m belong to the n2, which is this set, 2, 4, and etc., then m can be given as 2k. It is correct. This one correct. So in that case, okay, it is correct. Look, when m equal to 2k, just pay attention. I will put it there. F of m, look, f of minus k, look, f of minus k. So look, when m is equal to 2k, so which is positive, then minus k, actually minus k, look, minus k is minus m over k, m over 2, which is negative. If it is negative, we will use this. We will use this. So minus k, so it becomes what? Minus 2 times minus k plus 1, which is equal to 2k plus 1. You see? It should be 2 m. Actually, it should be m. Mk plus 1. So if f of k should be equal to m. So it means, so I should compute on minus k actually is a negative. If negative, if k is, why it is called m? So here little unclear things. So generally what they want to say, so d of f is equal to r of f. Actually, the domain of f is equal to range of f. So that is a surjectivity. Surjective, yes. Injective already proven. Surjective is proven. So it is, this function is bijective. So they are showing this example too. Actually, is a bijective function. If bijective function, then you see z, which is larger set than the n. They are equivalent set. So equivalent is actually depend on the finding of the bijective function. Okay, that's all. So I am going to finish because now it is already time. I hope you get the main point. So what I am going to do next week on Monday, because on Monday, Sunday I will finish chapter 2, and I will give you one quiz 2. Okay, be ready from chapter 2. Okay, Monday. Again, I am not choosing very heavy questions, simple questions. But we need to discuss. I think 1 hour I want to give. From if 12 to 1 we have class. After class can. So we discuss, okay, with Anne, and we find the timing, maybe evening, maybe afternoon, suitable time we will find, and we will sit for the quiz 2, okay, from chapter 2. So almost getting end. Unfortunately, today I also couldn't finish. Okay, that's all. If no questions, okay, if no questions, so finish. Anything? No question.
Doctor, for the quiz 2, the time.
Yes.
Time for the quiz is how much time? How much is the time?
Actually, for the quiz 2, because it depends on the proof, so I want to give 1 hour.
Oh, 1 hour, including the scanning and submitting.
For the scanning and submitting, half hours. So 1.5 hours.
Thank you, Doctor.
So that's why you need to find. I will discuss with Anne, and you will suggest and make it available for everybody. Okay, for the exam you have to come because it is online. Maybe not during the class, because during the class I have to teach the out of the class. Okay, please discuss next week, Monday, Tuesday, whatever convenient, you just let me know. Okay, so that's all. Thank you very much. If no questions, so here from auditorium also, our students not giving any extra questions, right? Bye bye.
Thank you, Doctor.
Thank you, Doctor.
And recording file, because this